So this video reviews demand forecasting. So demand forecasting was the first major topic we studied at the very beginning of this class. And so what are things I would like you to take away from this class on this topic, as well as, what are fair game in terms of the final exam. So one thing I think is really critical for you to remember and keep with you as you become a supply chain decision maker in the world are the kind of laws of forecasting. Specifically, that forecasts are always wrong. And I know we've talked a lot about that in this class, but why does that matter? Is that forecasts become an input to every other decision we did in this class. And so if you realize that your forecast has uncertainty, has variability, that will change some of your decisions down the line. And so I think that's fundamentally something you should always take away with you, is that forecasts are always wrong. Our goal is to be less wrong. Our goal is to try to make the most accurate model we can, but realizing they're wrong is an important thought, because that means we may have extra safety stock in terms of inventory. We may do different things than assuming these are exactly right. So I think that's a really important takeaway. I think it's also important to think about, okay, given all forecasts are wrong, given we know the impact of variability, that variability requires us to have more resources for the same service level, what can we do then in terms of operational decisions in forecasting? And a couple things come to mind. The first is that long forecasts are usually less accurate than short-term forecasts. So you should have both. You need to long-term forecast and short-term forecast. But oftentimes they use different data. They have different values in terms of uncertainty measures. And so you may have different information. And so you should usually have some combination of these things, but realizing you'll have less variability typically in a shorter term forecast than a longer term one. And then one way to reduce variability is to think about aggregate forecasts. So remember, aggregate forecasts are the sum over a bunch of different disaggregated things. So if you think way back to the beginning of the class, we did this poster project or activity where you had to each pick one of the three posters. And if you wanted to forecast for a specific poster, Tigger or Monet or whatever, no one got all of those right. But some people got the total number of posters demanded. And that would be an example of an aggregate forecast. So as much as you can produce aggregate forecasts, that's good for your company, because that reduces variability at the aggregate level. And so that's useful to know. And then the further up the supply chain a company is, the greater its distortion of information it receives. That's really the bullwhip effect. So now that you know some of the laws or kind of characteristics of forecasting, we studied in this class a very specific type of forecasting, which is called time series forecasts. And so as a reminder, what is a time series? It's just a collection of data on the x-axis is time, and that's a time series forecast. So as a reminder, what are the assumptions of time series forecasting? Is that the past is a good indicator of the future. So we are only using past data to predict future data. And so why that matters is it's really important to plot the historical data and understand the trends in your past data, because those trends, whether that means there's seasonality, whether that is an upward trend, downward trend, etc., those systematic components in your data are what's going to be showing up into your forecast, because again, time series is only using past data to predict the future. And so that's really critical, is you should plot and identify systematic components in the data, and then make sure you pick a proper time series forecast. So if your time series data has, for example, seasonality, trend, and a level, then picking Winter's method will ensure that those components show up in your forecast. If you don't pick a model that has those systematic components, your forecast won't have those systematic components. And so that's why it's so critical. And then once you do that, you can create the forecasting model. And so in this class, we did things like smoothing, exponential smoothing, moving average, Winter's method, etc. And so what does creating the forecasting model do with computational, with R? The main key thing is we need to set our input parameters. So for moving average, that's n, how many periods. For exponential smoothing, that's alpha. For exponential smoothing trend, that's alpha and beta. And so if you remember back to homework 1, we had to do 2 steps in our R. We had to first kind of set up the forecast, and we would get the best alpha or beta out, and then we called the forecasting function. And so the key here is creating the forecasting model is really about setting these input parameters. Then once we have the input parameters, so we know alpha, or we know that we should do a 3-month moving average, we can then use that model to forecast future demands. And then we should assess how accurate is that. And as we get more data, we should update our parameters and update our model, and then continue that process. So you should understand this process. You should understand what is time series forecasting doing. The major assumption is you need past data, first of all, to even do this. And second of all, past data will inform future. And so your forecasting method is not going to predict these crazy things, for example, with COVID, if it wasn't in the previous data set. And so that are some limitations, but time series forecasting is used quite a bit in practice today. So once you select an appropriate model of demand versus time, how do you do that, or how do you select that? Again, you need to understand what are the systematic components. And then if you can identify those, then you can pick a model that is appropriate. And so the ones that we studied in this class was moving average and simple exponential smoothing, which are the ones that only have a level. They don't have any trend nor seasonality. If your historical data has level and trend, but no seasonality, in this class we use exponential smoothing with a trend, also known as Holt's method. And then if your data has level, trend, and seasonality, we studied Winter's model. So note that these are just the iceberg of methods, but one thing you should be able to take away from this class as you go into the world is you need to find a method that matches with the systematic components. And then you should be able to understand if you go into your company's ERP system or different software, what these things mean. So I know at the beginning of class when we did this competition, some people were using R and they were like, why is my forecast giving me the same answer for every period? That's because it was a moving average or simple exponential smoothing, which means it only has a level going forward. So hopefully after this class, you can understand the outputs coming out of these software systems. You should also understand the measures of forecast errors and bias, and so there are a number of them. The key thing here is that you always need both a forecast and an observed data point. So remember, F of t is the forecast for period t, and D of t is the demand, the actual value in that period. And so to be able to actually calculate an error, you need both of those things. So one other thing I would like you to take away, this might show up on a conceptual question, is when can I calculate errors? And how do I do that? And so a lot of what we were doing at the beginning of the class is we were actually forecasting something that already had occurred. Well, you could ask, well, why do I need to forecast something that already has occurred? The reason is we want to use that to calculate these errors, and then we want to use this measure of error as our objective function. So we want to minimize one of these measures of error, and what are we changing? We're changing these input parameters. So we're changing, for example, alpha in the simple exponential smoothing. And so understanding why would you develop a forecast for something that happened in the past? Why do you do that? Well, we do that because we need that to calculate error rates. And so our assumption is if alpha of 0.5, for example, does well on past data, our assumption is it'll also do hopefully well on future data. And so we're setting these parameters using these measures of error. And to be able to do that, we need past data. Okay. And so, you know, one of the questions I think is important is how do you recommend which method is best? And so, you know, if you think about first of all, you have to figure out what method is appropriate. So if your data has certain systematic components, you need to make sure your method has that. But we studied multiple methods that both have, for example, level being the only thing. So a question could be, how do I know is exponential smoothing or moving average better for my data set? And then you could say, well, moving average, should it be 2-period moving average, 4-period moving average, 5-period moving average? How do we determine that? And so the short answer is we should try out these different methods on our past data set and see which ones do best, and then recommend the one that does best on past data. And so for a very specific example of that, let's say we want to figure out how many periods should our moving average be. And so remember, we should think about that moving average is a stationary forecasting method. So we're going to consider that our past data has only level. So if your past data had something else, this wouldn't be appropriate. And then you should pick the method with the smallest forecasting error. So you have to define how do we want to measure forecasting error. A most common one is MSE, mean squared error, but sometimes people use other measures. And so then we need to have both a calculated measure forecast, needs F of t and D of t. And so what you do is you need to be fair. And so if you remember back to homework 1 as well as exam 1, we talked about what's the biggest set that is fair. And that means you have both a 1-step in advance forecast and a demand point. And then you measure this using, an R for loop, and you pick the end that gives you the lowest error rate. And so, okay, that was a lot of detail. So what should you be able to do on the final exam? Forecasting will show up primarily on the conceptual part of the exam. So remember, the conceptual part is a combination of multiple choice, true and false, and essay questions. And so all of this is fair game. What I think is important is you really should understand the properties of forecasting. So you should understand those 4 laws of forecasting, that forecasts are wrong, aggregate forecasts are more accurate than disaggregate forecast, etc. But I won't likely just ask you to list them. I will probably give you a context so that you can understand them. You should be able to identify what is the right method. So maybe I describe some situation and I say what method is most appropriate. You should be able to actually use the equations to get a forecast. And I will say there are questions where you need to calculate a few things. They're relatively simple calculations. You should understand what Winter's method and the seasonal factors do and how it works. So I could think about things like the seasonal factors. You should understand that. You should be able to estimate parameters and create a forecast using R code. And for all of these different things. So there are a couple multiple choice true or false type questions that have R code, and it would say, if I wanted to do this, what would be the correct line of R code? So you should be able to do that. Remember, the exam is open notes, and so it would be good to review that ahead of time and understand again how to use R. You should understand and calculate measures of error. You should understand how to choose which forecast is best. You should be able to set input parameters to minimize these forecasts and understand what that means, and understand what is a training and a testing data set. So I know that's a lot. One thing to emphasize is a good way to study for this is to go look at your exam 1, exam 1 and homework 1, and remind yourself if you can do exam 1 again, you're likely in pretty good shape for the conceptual part. But it is cumulative, the final exam, and specifically the conceptual side will be tested on forecasting. And so why is forecasting really critical? Why did we start with that? Is that is the input to every other decision we made in this class. And so all supply chain decisions made before demand has materialized are made to a forecast. So I think it's important to realize how critical forecasting is and why is it critical? Well, we use this as an input to do everything else. And it also the impact of this. And so by definition, forecasts are wrong. By definition, we're inputting uncertain variables or uncertain parameters into our optimization models. And so understanding the implications of that and how we can deal with that is our topics kind of throughout the rest of the class.